still have a lot of stuff to go over to cover. So make sure we're recording with the voice. Start up the browser. Yep.
So the video is still not uploaded, the one that I uploaded last time. We're uploading it, still not uploaded on YouTube.
From what time again?
Was last Thursday. Was 13th, was it 13th?
From the 13th? Let me check. From the 13th. Okay, here's the 12th. And I have not. Huh. Okay. Unfortunately, we still have it here. I wonder whether something is wrong. Maybe something is wrong with the file, so it would not upload. So we'll try it again today and see whether it uploads or not. Because I think I tried it already. Maybe it was not. It uploaded, and then the file format has an issue, and it would not keep it on the YouTube server. So we'll give it a try today. It's not going to take long. It will take 3 minutes to upload it, so we can come back and check on it a little bit later. All right. It's interesting. YouTube is now using HTTPS and not just HTTP. So network administrators cannot see, what the employees are watching.
Maybe.
Not anymore.
Depends
Well,
on how much money they have.
huh?
It depends on how much money they have.
Oh,
It can be strict.
well, it can be, but the question is, how are you going to spend your money, even if you have that much money, right? And of course, with certain types of organizations, it's not their money to begin with, so it's okay to spend it on anything they want. All right. So what we'll do today is the first thing we'll do is to take the quiz for today, and I'm still talking funny because the gum surgery thing is still healing, so I still have that little appliance on my palate, which kind of makes talking a little bit strange. And what will be even stranger is after I take it off, because it's all done, then I'll have some time to adjust back to what it used to be. It will be out in about 40 seconds, and I'll give you guys, like, I don't know, 10 minutes, something like that to work on this one. You can work on it on a piece of paper. Make sure you write your name on the piece of paper, and then just turn it in to me after the 10 minutes or so. I don't think it's going to take too long. It's not supposed to be a long, difficult question. And it is closely related to what we talked about last time, as well as your homework assignments. So I don't think it's a bad thing to do. It's just a good thing for you guys to kind of warm up to what we'll talk about today, as well as the homework assignments. So here it is. Now it is active, and we can click on it. And this is the question. All right, so I'll just kind of briefly explain what it is asking. This portion here is basically a subroutine. We have the allocation of the local variable, the deallocation of the same local variable. There's only one 4-byte or 32-bit local variable. This line is here just to show you how we put a value into the variable, into the local variable. And then at some point, we have a push instruction because, for whatever reason, I don't even know why, I want to save register EAX for some purpose so I can use it later on. And then after that, I want to copy my local variable into EBX, okay, and do some more thing here. And then afterwards, at some point, I want to pop the saved EAX back into the register EAX to further do some more computation. So the question is, when I want to access the local variable at this point, how am I going to copy the local variable that is living on the stack into EBX at this point? That really is the question. Okay? And it's related to something that we talked about last time. Okay, last time we actually talked about a particular addressing mode that can be used, in this particular case.
So we're just replacing the question mark?
Yep, just tell me what the question mark is supposed to be. You don't have to rewrite the entire program. And remember, write down your name too. So I'll give you guys about 10 minutes, 5, 10, whatever. It's one of those things you either know it or kind of not know it. Okay, I'll give you guys an option. You can either use a single operand here, then you have to remember what we talked about because we introduced a new addressing mode last time, or you can split it into several instructions if you want to. So then you won't need to remember what operand we were talking about last time, but you still need to know how things are organized on the stack. So you have the option. Give you one more hint. So I'll give you one more hint. The call to subroutine F is going to push a return address on the stack. Okay? And then we get into the subroutine itself, right? So when we get into the subroutine itself, the next instruction we execute is subtract long $4 from ESP. So what that would do is to reserve the next 4 bytes, but it's not going to put anything there. And then all the other instructions will not change the stack pointer. So the stack pointer will now be pointing here. By the time we get to the push long EAX instruction, the stack pointer is still pointing here. So that means if we push EAX at this point, then EAX, or a copy of EAX at this point, will now be here on the stack, and then the stack pointer will be pointing to the least significant byte of the EAX saved on the stack. Okay, and that's the situation when we get to move L question mark EBX. So the question is, with ESP pointing to here, how do we get to the local variable and copy that to EBX? So that is kind of what the question is asking. Right? So I'm hoping this is helping a little bit.
You said instead of replacing that 1, we could do a series of commands?
You can do a series of instructions, yes. you ready? Yes? All right. Well, okay, so pass your answer back to me, and then I'll collect them all, and then I'll tell you the answer. Have I collected all the answers? All right. So very good. I can see, there are, some people use the simpler answer, which is, using a single special operand that we talked about last time, which is the based addressing mode. And some people use a series of instructions, which is also what we talked about last time, which also works, okay? It's just a little bit more cumbersome, but it is the RISC way of doing things. So either way will work. So I'm going to give you the solution right now, just so that you know what the answer is supposed to be. Okay, I'm going to use just a regular text WordPad here, Notepad. So the answer is either you can use this solution, which is the easiest solution. This is the easiest one. Okay, you're using the base addressing mode, which is something that we talked about last time. It's also in the notes that has been on Moodle since day one. This is the base addressing mode. What it does is it will take whatever ESP has, add 4 to it, so it becomes a new address, and it will go to that particular location, grab those 4 bytes, and copy those 4 bytes into EBX. So that's one way of doing things. It's the easiest way, but it's kind of a more or less a CISP way of doing things, because you are now using a CISP type addressing mode. The RISC way of doing it is to say, okay, let's copy ESP to some register that is not currently in use. Now, since I'm pushing EAX, that means EAX is probably useful for something, and I don't want to mess around with it. EBX is the destination, so we definitely don't want to mess around with EBX. You can actually use EBX in this case because you can overwrite EBX with a dereference, so you can use it both in the source and the destination in this case. So I'm going to use EBX in this case. You don't have to do it in your answer. If you use ECX or EDX, that's fine, not a problem. But I'm going to use EBX here because eventually it will be destroyed anyway. So in this case, it doesn't really matter. So I moved ESP into EBX, and then I can add 4, which is the displacement, to EBX. So at this point, after the add L instruction, EBX will now be pointing to the it will be pointing to the local variable. And at that point, I can do an indirect operand of EBX back into EBX. That is 100% okay. We have seen instructions like this already from Treasure, right? One of the, I think Treasure 2 already has an instruction like this. So it's perfectly okay to involve the same register in the first operand as well as the second operand, one being an indirect and the other one being a register operand. So that's perfectly okay as well. Okay, that's the second solution. All right. Are there any questions about these two possible solutions? I will score both as perfectly correct. Okay, so there's no penalty for using one or the other. Yep.
Is there a third solution?
Is there a third solution?
I thought you can just add 4 to ESP and then move indirectly to EBX.
Then you have to reset the stack pointer. Because if you add 4 to the stack pointer, you're quote-unquote permanently changing the stack pointer. Now, that is also dangerous because it will look okay for the most part when you're writing programs in a protected environment. But whenever you move the stack pointer, especially when you're moving it up or adding something to the stack pointer, you're leaving whatever is under it unprotected at that point. Because if an interrupt is to happen during that time, the interrupt will overwrite what we have already put onto the stack. So that would not be a very good solution. I mean, it works for the single purpose of doing this, but it will mess up the rest of the program. If you did not subtract 4 from the stack pointer again, after that sequence of instruction,
Yeah.
it will mess up the rest because the stack pointer is no longer at the right point of the program.
So would that be incorrect? Because it seems like the same thing you did at the top, move 4. and
Okay, so tell me what is the sequence of instructions?
I did add L $4 in the ESP,
Okay.
and then next line I did move indirect ESP into EPX.
Okay, and anything else?
No, that's
Okay.
that's what was asked.
So there are, as I said, there are two issues with this chunk of code here. The first issue is right after add 4 to ESP, if you're not running a program in a protected operating system environment, any interrupt happening right at that time will overwrite EAX that I have just pushed on the stack, that I intend to preserve on the stack. Do you see what the problem is?
Yeah.
Okay, so that's the first issue.
Yeah.
And then the second issue is there's no subtract 4 from ESP, so that means the stack is no longer balanced at this point. So for the single purpose of just doing that one single thing that I need to do,
Yeah.
it works okay, but by doing so, it is now causing, issues, down the line. So it would not be a good solution.
So it'll be wrong.
It'll be partially wrong.
Okay.
Yeah, it'll be partially wrong because it will definitely mess up the rest of the program, even if there are no interrupts. If you do a subtract 4 from ESP after that, then it will still be partially wrong because you still leave the part of the stack that you need to preserve open to being overwritten by ISRs, by interrupt service routines. Because the stack pointer is basically a bookmark, and it says, on this side of the bookmark would be stuff that I need to preserve, it's still in use, and on the other side would be stuff that is free to be allocated, free to be reused. So by moving that bookmark back one page, you leave a very small amount of time where that one page where EAX is actually saved onto is now open to be rewritten. So that's why you will still end up with that problem even if there's a subtract 4 from ESP afterwards. Okay. All right. So any other questions related to this little question? Pop L quiz question. No questions about this one? Okay. Alrighty. So I have been writing the solution for the exam itself as well as the grading rubric for that. So how many people have taken a look? Because it's already kind of posted online. Nobody. Okay, nobody's aware. Okay, it's here. So once it's done, I'm going to go over it. I'm missing one question. Question number 2 has the answer, but I have not disclosed the grading rubric yet for question number 2. So I will kind of defer talking about this one until later, until I have all the rubrics ready. But you are more than welcome to start reading it if you want to, because I passed the answers. I passed the paper back to you in the previous class, so you have your own paper. And now you can kind of compare your own paper with the key, and then use the rubric to kind of guesstimate how many points you'll be getting based on your own answer. So that would not be a bad thing to do. I know it's going to sting a little bit sometimes, but it's not a bad thing to do because you have a kind of an assessment of your own score of your own test given the key. Question number 2 is the only one that does not have a rubric yet, but you can definitely kind of grade yourself based on based on what the key is and also the rubric for question 1 and also question 3. Okay. Any questions about that? It took me almost all night to come up with the rubric. Coming up with the key is easy. That's like bam, done. But trying to determine the grading rubric, that's the one part that takes a little bit longer. All right. So if there are no questions about this, we are now moving on to topic 8. Go ahead.
YouTube video. See what it's
Oh
like.
yeah, it's converting right now. It says it will be published at this location. So right now it's processing. Sometimes if the file format has an issue, it will fail the processing part, and YouTube will come back and say sorry, I cannot convert. This is an unknown format to YouTube, and it will not be able to post it. In that case, the one thing that I can do is I can use some of my own tools and see if I can rescue the file and at least get back some of the content on the video file. It may be possible. I don't know for sure. Right. So we'll keep an eye on this one. But thanks for reminding me. This is still up and running. All right. So what we'll do today is we're moving on to topic 8. What we did last time was a good introduction to topic 8. And what we went through today for the quiz is also a very good introduction to topic 8. So topic 8 is about the call frame. And a call frame is basically a construct on the stack that is created on a per invocation basis. Okay, so each invocation of a subroutine will end up with a construct on the stack that we just call a stack frame. Okay? And on the stack frame, there will be quite a few items. Okay, but some of those items you should know already because of cisp310. Parameters to a subroutine on the stack, local variables on the stack, return address on the stack. The only one thing that we have not talked about that would also be on the stack is called a frame pointer, which is not the same as a stack pointer. So in order to understand why there is such a thing called a frame pointer, let's go back to the quiz for today. And it's right, today is the 20th. So the quiz is here. Okay. So I'm going to open this up here on a tab here because I need to refer back to the other one. So the problem with this instruction here, or this operand here, is I have to keep track of all the push and pops on the stack in order to figure out the right offset to the local variable. Does everybody understand what I mean by that? Because the more stuff I push, the further the stack pointer is away from the local variable. And as I push and pop, and then push some more and pop some more, because of the need to save and restore registers, the displacement or the distance between where ESP points to, the stack pointer points to, and where the local variable is going to float. And I have to manually keep track of the program to adjust for that, which is not very nice. Okay? Because at some point, if I go back to a program and at one place and I say, oh, you know what, I need to save a register here, it will impact every single access to local variables thereafter, that instruction. The same thing happens when it insert a pop instruction, because that will also change the displacement to local variables. So what we want to do is to say, okay, I'm done with having to manually keep track of all this, or the displacement, which is floating. I want to make a fixed point, okay, a pointer to point to a fixed place on the stack and say displacement to local variables and parameters will not change because this register is always going to point to this one place on the stack as far as local variables and parameters are concerned. Is that okay so far? What I want to do, okay, is to have a fixed point so that it doesn't change. So what I'll do is I'm going to use this as an example and give you the solution to this particular one using what we call a frame pointer. So this way you can kind of see side by side how the two code compares. So we'll still have an entry point called F, but now instead of subtracting 4 from the stack pointer and whatnot, the first thing I do is to push a register called EBP. EBP stands for the base pointer. Okay, EP is the base pointer, and E stands for enhanced mode base pointer. That is our frame pointer. EBP is our frame pointer from here on. So I'm save the frame pointer, and the reason why I'm saving the frame pointer is the frame pointer is being used by the caller of this subroutine as well as a frame pointer. So if I try to modify the frame pointer before I save it, there won't be a way for me to restore it so that I will mess up my caller. Okay, I won't mess up myself, but I will mess up my caller. So that's why I'm saving the frame pointer at this point. Now don't copy the way I'm typing the program, because I'm typing the program in a way that is structural but not sequential. Okay, so if you try to copy it the same way that I type the program, it's not going to work out very well unless you leave a lot of space in between everything. So what I do is, before I return, I'm going to restore the frame pointer so that to the caller of this subroutine, the frame pointer has never changed at all. And then I'll be ready for the return instruction. So everything that I want to do inside this subroutine will be between the push EBP and the pop L EBP instructions, because everything in between, I can modify the frame pointer any way I want at this point. And as far as my caller is concerned, all of that change is hidden because I saved it to begin with and then I restore it at the end. Is that okay so far? Okay. So right after I save EBP, then I say, oh, you know what? It is mine now. I can now change the frame pointer. So the only thing I do here is to copy ESP into EPP. In other words, when you look at the stack, instead of having the stack looking like this, we'll have the stack looking like this. So call F, which is from the caller, is still going to push the return address on the stack. But the first instruction inside the subroutine is not to reserve for the local variable anymore. The first instruction is to push EBP. So push L EBP with % symbol here is going to say what I call the old EBP, or the EBP that belongs to the caller of this subroutine. So that is now saved on the stack. And then after that, I copy. So at this point, the stack pointer is pointing here because that is the last item that I push on the stack. And then right after that, I copy the stack pointer without dereferencing it. I just copy the stack pointer itself to the frame pointer. So that means at this point, the frame pointer EBP will also point into this location. Is that okay? Because every time you copy a pointer to another register, that means we have two registers pointing to the same location. So now, at this point, we have the frame pointer and the stack pointer pointing to the same location. But that is what the frame pointer is for, okay? Once I set the frame pointer for this invocation, I will never change it again. I will do all the additional push and pop instructions. I'll do everything with the stack pointer after this, but the frame pointer stays put. It's always pointing here. Are we doing okay so far? And then after this, after I initialize the frame pointer, I am going to, don't copy this either because this is the end also. So I have a matching instruction at the end of the subroutine to restore it, okay? So that I can restore everything in one single step. But I'll explain that when we get to that point. But at this point, I'm going to do what we did before, which is subtracting 4 from the stack pointer to reserve for my local variable. So by doing this, okay, the next instruction is so push L, and then move L, E, S, P to EBP, ends up with EBP pointing to the same location. And then the next instruction is a subtract long $4 from ESP. So what that does is to reserve 4 bytes for my local variable. So I would have 4 bytes, which I have no idea what would be the content at this point because it is not initialized. But which register is being moved?
ESP.
Only ESP, right? EBP stays put. So at this point, ESP is moved in pointing this place. But EBP is still here. That is the nice part, because from here on, I can do any push and any pop. It's not going to change how far the local variable is from where EBP points to. I do not use ESP anymore to access the local variable. From here on, I'm going to use EBP as a reference point. Does everybody understand the rationale of using a frame pointer instead of relying only on the stack pointer? Okay. Yep.
So why did we have to push the frame pointer onto the stack?
Because the frame pointer is also being used for the same purpose by the caller of this subroutine.
Oh,
so if I don't do
back.
that, then the caller is going to be upset about it and go like, hey, I'm pointing to the wrong place of the stack now.
Okay, makes sense.
Which sometimes happens when you have a C subroutine to write beyond the boundary of a local variable array. Sometimes you can mess up the saved location of EBP. So the subroutine itself is not messed up, but it will mess up the caller of the subroutine because EBP is no longer pointing to where it is supposed to.
Gotcha.
Okay, so from here on, the rest of the instructions will be pretty much the same. Okay, so I can say move L $5 into my local variable. But where is my local variable now? My local variable is, even though it is pointed to by the stack pointer, remember what I said earlier, I don't want to use the stack pointer as a reference point anymore. I only want to use the frame pointer. So compared to the frame pointer, it is still pointing to the same old location at this point. Where is my local variable? How many bytes is it off from where EBP points to? 4, or is it -4? It's -4 because it's pointing, it's 4 bytes below where EBP points to. So the move 5 into ESP is now becoming move 5 -4 as a displacement from where EBP points to. But you will probably remember this because from here on, this is my local variable. I can push, I can pop all day long, and this will still be my local variable because none of the push or the pop instruction is going to change EBP. So I can keep using this particular operand to refer to my only local variable from here on. Is that okay? So let's go ahead and just kind of finish this code here. Because I do want to give you the entire code just so that you know what it looks like. So at this point, I can push EAX on the stack. If I need to copy my local variable into EBX, that's all I need to do. Because the push instruction does not modify EBP, so I will still be able to access my local variable using EBP as a reference point and not really care whether I have additional push or pop instructions. So I can do another pop instruction here. And to end this program, interestingly, this I don't need to do this anymore. Okay, adding 4 to the stack pointer does not need to be done anymore because this is actually doing the same thing. When I'm all done, I'm going to say, okay, make ESP point to where EBP points to. So ESP, even if it is all the way down here, okay, it doesn't matter because I just use one single move long instruction and make it point to the same location from earlier, which is the saved EBP from my caller, and then right after I copy EBP to ESP, I do the pop long instruction, which is correct because at that point it should be pointing to the saved EBP that I did earlier. And then I'll be able to return because the return address is right about that. So, are there any questions about how I modified from the quiz question itself, which is kind of problematic in a way because I have to adjust for all the push and pop instructions, to the use of the frame pointer, which means it is now immune to all the push and pop instructions? Any questions about that? No questions? All good? Okay. So that takes care of local variables. What about parameters? How do we pass parameters into a subroutine? So let's go ahead and take a look at a subroutine. Okay, so we'll take a look at Factorial. Okay, so here's my Factorial subroutine. It takes a number n, and I'm hoping that most of you, have seen this more times than you really want to see Factorial being abused as an example of a recursive subroutine call, but we'll go ahead and do it anyway. One more time, okay? So how do we express Factorial as a subroutine? Do you guys want the conditional statement version, or do you want the ternary operator version? Ternary operator, the question mark and the colon? You want that one? Okay, let's do it that way. So the ternary operator is going to use a single return statement, and the return statement involves a ternary operator expression. So this is a good time to refresh your memory about what is a ternary operator, because you will see that in industry. People do use that particular operator in industry. So it has 3 components separated by a question mark and a colon. What goes to the left-hand side of the question mark is a condition. Okay, so whatever expression you put here is a condition. So in this case, the condition is n greater than 0. Okay, if n is greater than 0, this expression is evaluated and returned. Is that okay? So it's kind of like an if-then-else, but in the form of an expression. So I have the if already, which is the n is greater than 0. This is the then. Okay, if n is in fact greater than 0, I want to return this expression, and this expression is n times the factorial of n minus 1. This is the else. Okay, in other words, what if n is not greater than 0? Then we return whatever is now being highlighted in the text editor. And that would just be a 1, because the factorial of 0, by definition, is 1. There's only one way to organize nothing. That's basically what factorial of 0 means. There's only one way to organize nothing. Are we doing okay so far? Yep.
What happens if you pass it a negative number?
It will still be 1. It's not really reasonable to ask for the factorial of a negative number, but this subroutine would not fail. It would just say, it's 1 also. Yeah, there's one way to organize a negative number of things. All right, so is that okay so far with this subroutine? Okay, this is the recursive subroutine. You can always rewrite it back into the conditional form, but I'm just going to use this one as an example. All right, so the question is, how am I passing parameter n into the subroutine? And most people would say, well, based on everything that we have talked about, the easiest thing that we can use in this case is a register. Let's pick EAX. And you would be partially right, okay? Because a register is quick to use, okay? It doesn't involve accessing memory whatsoever, so it's really fast to use. And it is something that the subroutine and the caller both have access to, okay? But there's only one problem with using registers to pass a parameter. What if the parameter is a structure and it has hundreds of bytes, and you're passing a by value? Then we have a little bit of a problem, right? Because then how do you use registers to store hundreds of bytes? I mean, we do have with a 64-bit architecture, and assuming we have 8 registers, we can at the most specify 64 bytes. That's all we can do, which is not a whole lot. So what we have to do is to say, okay, it's not going to work if we just use registers to pass parameters. So what else do you think we can use? The stack, exactly. So we can use the stack to pass parameters as well. Okay, so let's think about the order of things. Do you think the caller, from the caller's perspective, do you think the caller should put the parameter on the stack first before the call instruction, or do it in a reverse way? Call first and then pass, and then put the parameter on the stack. Just logically, which way makes more sense? Okay, when you call, the control is transferred into the subroutine already. In other words, right after the call instruction, it will save the return address, and it will be in the subroutine that you are calling already. So as a caller, you won't have control until the subroutine returns. So that means by the time it returns to you, it's too late to specify the parameter. So the correct order is to specify the parameter first on the stack, and then do the call. Is that okay? All right. So what we'll do here is we'll go ahead and have 2 subroutines so that we can see both from the caller's perspective and the callee's perspective of what is happening here. G is a pretty useless subroutine. It does not return anything, and it does not take any parameters, but it does have a local variable. So we'll just call that local variable int x, okay? And we'll just say that x is the factorial of, for this purpose, it's not really important which number we want to find the factorial of, so we just say we find the factorial of 0. That's all we're going to do in G. So now we want to look at the code, the assembly code for G and as well as for factorial. Okay, but we'll look at G first because we want to see how things look from the caller's perspective first. So I'm going to use another mouse pad for the assembly code. So this way we can look at the C code and also look at the assembly code at the same time. So mouse pad, another mouse pad. Okay, so our focus right now is to look at subroutine G. Subroutine G is going to be written in assembly right now, and the single entry port has a symbol name called G. That's all we need to do to identify this is a subroutine, this is the entry port. And we are going to use the new standard. We're going to use the frame pointer. Okay, we have one single local variable in G, and well, we know how to deal with that already because we just talked about it, right? So we'll go ahead and use that sequence of instruction, push out EBP to begin with, and I will try to write it in the sequential way, but when I write something in the sequential way, sometimes I forget to close it properly, so I have to be careful about that. Okay, so we push EBP to save the frame pointer of my caller, okay? The caller of G is not clear from this code here, so it can be main, can be whatever. So we save the frame pointer, and then the next thing we do is we copy the stack pointer into the frame pointer, because at this point it is okay for me to overwrite the frame pointer because I can now restore it later on from the stack before I return to my own caller. Is that okay? All right, so this is the stuff that we have talked about already, nothing really new at this point. And then we subtract 4 from the stack pointer. Basically, we are now reserving 4 bytes on the stack for local variable x in G. Also, something that we just talked about is just that in the previous example, I did not give a name to the local variable. In this case, I call that x, okay? And then we have to call the subroutine. Because when you look at the line x equals to the factorial of 0, I can't really do anything about x until I know the return value of factorial. Is that making any sense? So I have to call factorial first. But I just earlier talked about how you have to specify the parameter on the stack first before you call the subroutine. So the question now is, how do we specify the parameter on the stack? Pushing a 0, exactly. That will do the trick. Okay. So in a cisp environment, this is the thing to do. If you do this in this class, it will actually compile. Okay, you can actually push long immediate with the cisp instruction set that we have. But if you don't want to do it in the cisp way, there's always a longer way to do it. You can always put a 0 into register EAX, and then push register EAX on the stack, which also effectively push a 0 onto the stack. But it's one more instruction. It's not that much more expensive because move 0 into EAX is a very, very inexpensive operation. It does not access memory whatsoever, so it's a very, very low clock cycle type of instruction. Push L is the long one, okay, and you have to do it anyway. So separating it into 2 instructions in a RISC way is not such a big deal. It's not too much more expensive compared to the first approach. But this is how we push parameters on the stack, okay? You just push it on the stack. And once we specify the parameter on the stack, we can now call the subroutine factorial. Okay, so here's factorial. When factorial returns, I got 2 things to do. The first thing is factorial as a subroutine will mess around with its own local variable and whatnot if it has any, but it won't do anything about the parameter. Okay, the parameter is not the job of the subroutine being called, or the allocation and deallocation of the parameter is not the job of the subroutine being called. It is the job of the caller. So when we come back from factorial, do I still have any use of that 0 on the stack that was the parameter to factorial? That's not useful anymore. So I want to deallocate those 4 bytes from the stack. How do I deallocate 4 bytes and not having to restore that those 4 bytes into some register? Adding 4 to the stack pointer, exactly. So this is what we'll do here, is to add 4 to the stack pointer, just so that we can toss away the 0 that is on the stack, which is my parameter. The next one is, but what is the result? Okay, factorial is supposed to return a 32-bit integer. Where is that 32-bit integer? We have been using a particular convention in this class. What is that convention? Sorry? It's in a register, and which register have we been using? The A register, EAX. Okay, so that means that at this point, EAX already has the result, which is the factorial of 0. I just need to store it into my local variable x. So a single move instruction will do that because EAX is just a register. The second operand is going to be a memory operation because it is at a displacement of -4 from where EBP points to. Now I do understand that at this point ESP is actually at the same place, but you know what? I'm not going to use ESP to refer to local variables or parameters. Am I still doing okay so far? Okay. So as you can probably see right now, it is the end of the subroutine. So at the end of the subroutine, I'm going to restore the stack pointer from the frame pointer. So I copy the frame pointer back to the stack pointer, and you can see how this instruction here is the inverse of this one here. It's exactly the opposite of it, because we are now undoing, we're unwinding stuff. So we are now restoring the stack pointer from the frame pointer, and effectively in this particular context, effectively what it does is it is just deallocating the 4 bytes that I have used for the local variable. That's all it's going to do. And then after that, I know the stack pointer is now once again pointing to the saved frame pointer from the push L EBP instruction at the very beginning of the entire subroutine. So now I'm ready to pop EBP from the stack to restore the frame pointer of my caller. Okay, because at this point, I don't need a frame pointer anymore. I'm all done. So I just need to restore the frame pointer to whatever value it was so that my caller will not notice that the frame pointer has changed. And when that is done, the stack is now pointing to the return address, which means I'm ready to execute the return instruction at this point. Are we doing okay so far from the perspective of the caller of a subroutine, how to pass parameters on the stack? Yep.
Could you explain the line 4 from the bottom again, please?
You mean adding 4 to the stack pointer?
Move L EAX, yeah. Or subtract.
The one before, after that?
Yeah, move L EAX, comma, -4 EBP.
And you have question about the second operand itself?
Just what exactly that's doing, the -4, because the
Negative?
yeah.
Okay, so you have question about the second operand. The second operand is specifying, this is the base addressing mode.
Right.
We are adding whatever the displacement is, which is on the outside of the parentheses, in this case -4. So we are adding -4 to EBP. We're not changing EBP, we're just computing the sum of whatever is outside the parentheses to the value of the register at the time this instruction is executed.
Okay, so it's essentially like subtraction, and it's referencing the next value.
It's referring to the 4 locations starting at the location of EBP -4.
Thank you.
It's called the base addressing mode, which is also what the one of the accepted answer of the pop quiz was. That's basically the same type of operand. All right. So this is from the perspective of the caller. Now let's take a look at things from the perspective of the subroutine being called, which is factorial. Okay, so here's factorial, the entry point. And the way I usually do things is I do it in paired. So as I said, I do it in a structural way. So whenever I define the entry point label of a subroutine, I automatically insert a return. You cannot imagine missing just the return instruction, what kind of trouble you can get into. Because if you don't have a return after a subroutine, the compiler or the assembler doesn't care. The assembler is going like, oh, there's no return instruction here, so I'll move on to whatever the instruction is right next to it. And guess what? That can be the beginning of the next subroutine. So calling one subroutine is almost like calling the subroutine and then calling the next subroutine, whoever is next to it, which can cause major confusion. Okay, so that's why I personally always put the beginning and immediately insert the end, and then go back and insert whatever is supposed to be in between. That's just a personal preference. You don't have to do it the same way. But I'm just telling you, after being burnt many times by not remembering the return instruction, I found that this way is a very inexpensive way to make sure that I don't make that mistake. And same way, here I push EBP and I immediately say, okay, at the end I'm going to have to pop EBP. Same thing, so that I don't forget to do it. Right? All right. Now we don't have any local variables here, so just move out EBP to, the other way around. So I take a snapshot of the stack pointer and now call that the frame pointer. At the end, I do exactly the opposite, copying the frame pointer to the stack pointer before I do the pop L. So I'm doing things in an opening and closing fashion, and this way I don't forget to do something, and they're always going to be done in the right order. Okay? So now we can actually talk about, what about the subroutine? What about the return statement and the ternary operator? Well, the first thing the ternary operator has to do is to look at the parameter n and compare that to 0. So the question is, at this point, where is my parameter n on the stack? And I want to use EVP as a reference point. Well, let's take a look at the stack. So what I would do is I'm going to, I can use another editor here. So I'm going to put this one over here because the actual ternary operation is not important at this point. So I'm going to use another instance of mousepad to show you what is happening on the stack. Okay, so we'll start with the caller. Okay, so from the caller's perspective, which is G, we have essentially push 0 instruction, right? I mean, I move it into a register EAX first and then push EAX, but as far as the stack is concerned, that's all we are doing. Okay, we're pushing a constant of 0 on the stack. So we have 0, 0, 0, 0, 4 bytes on the stack, and the stack pointer is now pointing to the least significant byte of those 4 bytes. After the push L instruction, I'm talking about this instruction here. Are we doing okay so far? All right. So the next instruction is the call instruction, right? So the next instruction is call factorial. I'm just going to abbreviate it to call fact, okay, just so that I have enough space to also show the content on the stack. The call instruction from G is going to push the return address on the stack. The return address is a 4-byte thing, so now the stack pointer will be pointing to those 4 bytes because it always points to the last thing that I push on the stack. Is that okay? Because I'm just tracing the program line by line, instruction by instruction, and try to examine what is happening on the stack as I execute these instructions. Once I call the subroutine, control is now in the subroutine itself, so I'll be on the first line of factorial, which is push L EBP. So once again, I'm pushing something on the stack, and this time I'm pushing the old EBP on the stack, or the frame pointer of the caller onto the stack. And as a result, the stack pointer is going to point to old EBP. This is at the point of the push L EBP instruction of factorial. Is that okay? All right, so after that, we have a move L ESP to EBP instruction, which doesn't really put anything new on the stack, but what it does do is now it will say, you know what, we got 2 pointers pointing to the same location because I'm just copying ESP to EBP. So EBP is now pointing to the same place that ESP is pointing to, which is old EBP. All right? So at this point, I'm ready to specify my next instruction to examine or to compare parameter n with 0. Where is parameter n at this point? It's those zeros, right? The 0, 0, 0, 0, 0, 0, 0, 0, that's my parameter n. So how far are those 4 bytes away from where EBP points to? I don't really care about ESP anymore because I can have additional push and pops. I don't really care about the stack pointer. But what about the frame pointer? They're 8 bytes away, okay? So that means, right at this point here, in order to compare n to 0, I can now say compare long, and 0 is just a constant, so we can always use the immediate operand here. I'm now implementing the return instruction, which is a little bit long by itself, but that's okay. All right, so now we are comparing long with parameter n, and parameter n is 8 bytes away from where EBP points to. So that's how we can access parameter n. Are we kind of doing okay so far with this code? So after the comparison, we have to deal with the result of that. If n is not greater than 0, so if not greater than 0, and because I used int here, which is signed, I also have to remember to use g and l here to match the sign of the parameters. So I say j and g to else, okay, and else is going to be here, and this is how I write my code. I always use do it in a structural way, so this way I don't forget to do something. Okay, then I go back and fill in the content of okay, what are we supposed to do for the then portion of the ternary operator? Oh, we need to multiply the factorial of n minus 1 to n. I know we haven't really talked about the multiply instruction, but the first thing we do is not to multiply. What is the first thing we have to do? Find out what is the factorial of n minus 1. So how do we do that? Is there a subroutine that I can call to find out the factorial of n minus 1? Factorial itself, right? Cool. Recursion, right? So how do I do this one recursion? Now this part is a little bit tricky, but I wouldn't call it like extremely tricky. The first thing I need to do is to compute n minus 1. I don't want to subtract 1 from n. I just want to find out n minus 1 as an expression. I don't want to do anything to the parameter n itself. So what do? Easy, right? We copy parameter n into, say, a register first, EAX. Then we can do whatever we want to EAX and not modify the original parameter, which is the intention. And then what do? We need to compute n minus 1. How do we compute n as n minus 1 now that n is in EAX? Subtract long $1 from EAX. Okay, subtract long $1 from EAX. Whoops. There we go. So now EAX is n minus 1, and how do we call factorial again with EAX being n minus 1? Yep, push long EAX, and then just do a call, right? Call factorial. That's recursion in assembly language. Now that we are, okay, when factorial returns with the result of the factorial of n minus 1 in EAX, the first thing I'm going to do is to say, oh, you know what, that parameter on the stack, we don't need it on the stack anymore. Let's go ahead and deallocate those 4 bytes. So this time we are dealing with ESP because we are essentially popping, but we are not going to pop the content on the stack to any register because nobody really cares about n minus 1 at this point. So I'm just tossing it away, moving the stack pointer. And now we are ready to do the actual computation. Now the computation of multiplication, which is not really the main focus of this particular exercise, is kind of funny. Okay, the mul instruction, which is MULL, multiply long instruction, is really funky because it only takes 1 parameter. Well, don't you need 2 things when you are multiplying? You always have 2 numbers that you're multiplying. So how come it only takes 1 single parameter? Sorry?
Yeah, there's implicit.
Yep, because one of the register or one of the parameter is implicit. It is EAX. So EAX is automatically one of the numbers of the multiplication. So you only have to specify the other number that you're multiplying to EAX. Okay? So that means, oh, you know what? That is really cool because EAX just turns out to have the factorial of n minus 1, which is the one side of the multiplication already. We just have to specify the other side, which is n itself. So we can now say, oh, that's just 8 bytes away from where EBP points to. That's our parameter n. So that's what we need to do here. Okay, that will do the multiplication. The side effect of multiply is also worth mentioning. Where am I storing the product? Nope. It is implicit. Okay, so EAX is one of them. Okay, EAX stores bit 0 to bit 31 of the multiplication of the product, EDX stores bit 32 to bit 63 of the product. Because when you multiply a 32-bit number to a 32-bit number, you end up with a potentially 64-bit number. And the multiply instruction does compute a 64-bit product by storing the lower half into EAX, which is implicit, and the upper half into EDX, which is also implicit. So you have to be extremely careful with the multiply instruction, because if you have been using EDX for something, to store something that you need to preserve, it will overwrite it. And most people forget that it will also modify EDX and end up with the program crashing because they thought multiply does not change EDX, but it does. Okay? And this is tracing the root all the way back to the Intel x86 architecture being a special purpose register architecture. Each register has a special purpose, or I should say certain instructions can only make use of certain registers and they can be implicit. So that's basically what we're getting today. So after the multiply instruction, we don't need to use EDX because we only care about the least significant 32 bits, and we are not using EDX for any purpose here, so we can just kind of leave it alone. Now, whether the caller is using EDX or not, it's a whole different story. In other words, Factorial is now modifying not only EAX, but also EDX. Am I making myself kind of clear? So if your caller is also using EDX for something before calling Factorial, that EDX is going to be modified. If you want to be absolutely safe about doing something like this, you can always do a push and a pop surrounding the multiply instruction. So you do a push EDX before and then do a pop EDX after to preserve the content of EDX, because we really don't care about EDX, but it will be modified by the MULL instruction. Okay, so but for this particular program, it's not a main concern, so we are not going to do that. Okay, so after the multiplication, that is going to be my return value already, right? So I'm all done with the then branch. We can jump to end if. What about the else branch? What are we doing for the else? We have a return value of 1. So how do we specify a return value of 1 in a subroutine? Okay, we know it's involving moving 1 to somewhere. Where am I moving it to? EAX, exactly. So that's my entire subroutine. Are we kind of doing okay so far with this particular subroutine? Okay. Let's go ahead and try it out. Are we ready to kind of give it a test spin? Okay. Take it out for a test drive. So we're going to take it out for a test drive. But unlike most test drives, where they just drive around, around the dealership, on a straight and level road, we're gonna take this Jeep all the way to some rough terrain and test it out. We'll test out everything by calling this subroutine in a C program and see whether it works well with a C program. All right, so we'll do something kind of fun this time. And what I'm going to do is I will open up a new file, create a new file here. And the new file is just going to be the Factorial subroutine. Okay, nothing more, just that. So we'll go to Untitled 4 and save this file. I'm going to make a folder for this first. So we'll go ahead and make a folder called Factorial. So I have a place to save this file. So I'm going to save this file into the Factorial subfolder. And I'll save this file as factorial.s, just so that it is conventional to use lowercase s for a assembly language program. And before we move on, I'm going to have to do one more thing. .text is not really required because .text is the default section. So unless you switch between .data and .text all day long, you don't really have to make sure that you're in .text or the text section or the code section. But we do have to do one thing here. We have to use .global to export the label Factorial. What this does is it informs the assembler and say, when you're done assembling this file, this particular label might be needed by the linker. Let the linker know about this label. All other labels like else and end if and stuff like that, they're not exported, which means that no one else, no one other than this file can see else and end if. But Factorial, being .global or using the .global directive, I'm now telling the assembler, hey, export this label. The linker may need to see this one. Is that okay? All right. So here's my Factorial.s program. We'll double check and make sure it's saved, because if it's red, that means I did not save it. And we'll now work on the C portion of this program. The C portion is pretty easy. We can just do a include standard io.h, so I can use printf, and we'll do a very easy main program. Whoops, I forgot I'm not using VI. That's the keystroke sequence for VI to go back to the previous line and open a new line. And all we will do is really just to call printf. Okay, printf, give me a base 10 signed number, print a signed number in base 10, and we'll check out Factorial. Do something that's a little bit more fun, Factorial of 3, and do a return 0. This won't compile because the compiler does not know what is Factorial, so we'll do a prototype to let the compiler know that Factorial returns an integer and has one integer as a parameter. Is that okay so far? So as far as this file, which is main.c, I'll call it main.c, is concerned, the compiler, the C compiler, is perfectly happy about it, because I have already used the prototype to let the compiler know, assume there is a Factorial subroutine of the name Factorial. It takes a 32-bit integer as its parameter, and it returns a 32-bit signed integer as its result. As far as the compiler is concerned, now it knows everything it needs to know to call and make use of Factorial. So on the line of the printf, the compiler would do its thing and say, okay, assuming Factorial is a subroutine, blah, 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 this is how I can use it. Okay, so now we have a program broken up into two pieces. One piece is written in regular C, not C++, just regular C, and then the other piece is written in pure assembly code. So now I want to say, can this program work? Can we have a subroutine written in assembly, somewhat understanding how parameters are called and stuff like that, and have it work with a C program? Okay, so let's go ahead and save this, and then we'll go ahead and take a look at how do we compile this program and get it to work. So now we have main.c as my second file. And for the linking and compiling, I'm going to drop down to a command line prompt here. So we have two source files. As it turns out, GCC knows how to assemble as well, okay, which is kind of cool. So we say that GCC-G to include debug information, -C, which means I only want to have the object file output. I don't need the executable right away. So the first one I'm compiling is just a C code, which is main.c, not a problem. GCC-G-C, Factorial.s, and a file not, okay. That has to do with mousepad not automatically inserting an end of line at the very last line here. So now, going through VI, I'm making sure there's an end of line there. Okay, so let's do that again. No complaints this time, okay? So that's good. So what we have now are two object files. Factorial.o is one object file, or object code file, and main.o is the other object code file. Does everybody understand what is an object code file as opposed to the source file? Everybody understand that part? Okay. So now I can link it. Instead of using LD to link, I'm going to use GCC for linking as well. So I can use GCC to do the linking, and this time I can say, okay, after you link, give me an executable called just main, okay, with no extension. And then the two object code file that I'm linking is main.o and factorial.o. And the linker does not complain because factorial.o as an object code file is exporting the label factorial, which main.o needs to know. Okay, but the linker is saying, okay, I'm doing the cross-referencing, it's not an issue. Okay, so now the question is it going to work? How many people think it's going to work, it's not going to crash? We can just run it from the command line and it should print 6 because 6 is 3 factorial. Okay, I'm not so sure myself, but we'll go ahead and try it first. So main, it does print 6. Okay. Now the next question is, if it does not print 6 and it crashes somewhere, can I debug a program like this using GDB? So that's the next question. So I'm going to say I will use GDB main, and I'll say let's put a breakpoint into the assembly code file. Okay. Now, but we have 2 files. So which file are we in, and how do we designate something in the other file? You can always say, list, instead of just the line number, you can always name the file that you are listing. So in this case, we are listing factorial.s starting on line 1. So you can always do that. So you can now put a breakpoint on line 3 of factorial.s. So we can say breakpoint at factorial.s line 3. All right, so now we're going to run the program, and now we're breaking on, well, not line 3 because, hey, it should be breaking on line 3. It's not doing that. The reason why it's not doing it is because it actually understands, what the first 2 lines are about, and it does not, it knows it's the entry point of a subroutine. Okay, so at this point, we want to know whether 8 bytes away from where EBB points to is really our parameter. And tell me again what is supposed to be our parameter n at this point. This is the first invocation of Factorial.
3.
Should be 3, right? Okay, let's check that. So the x command or the examine command is really useful for this purpose. So we say x slash and one thing only, and it's going to be a 32-bit thing. When you want to specify a 32-bit thing in GDB, it's a W. I know it's awfully confusing, but that's how they choose to name the 32-bit thing in GDB, which is inconsistent with the assembly language itself, but that's how we can do it. And then the location is EBP as a register plus 8. And sure enough, it has a value of 3. Okay. So at this point, I'm going to continue execution, and it comes to another breakpoint. Why is it breaking again in Factorial? The second invocation, exactly. So if I do the same thing with the examine command, I should see 2. If I continue execution again, should see 1, and the last one should see 0. Okay, which is this one here. Continue execution, and now it is a 0. Okay. Remember what I talked? Did I talk about backtrace in this class? Probably not yet. Did I?
No.
No? Okay. Backtrace is a really cool command in GDB. It allows you to see all the call frames on the stack. Okay. So I'm going to do a BT and see whether it will work in this case. It may not work because the assembly code. Oh, it does actually. That is really cool. Backtrace is really cool because it tells us how we got here in the first place. So in this case, it tells us that in main.c on line 7, it calls factorial. Okay, that's what the frame number 4 is. On line 7 of main, it calls the subroutine factorial. In the subroutine factorial, on line 10 of factorial.s, it is calling factorial itself, which is here. And you keep doing this, and right now we are in factorial again on line 5. And does anyone want to know how backtrace works? How can it determine at runtime, okay, how to trace back the entire structure of the stack and the call history that got us here in the first place? How do you think that mechanism works? And it has everything to do with what we are currently talking about today.
Goes through the stack and looks for return addresses.
The return address is important to find out, which subroutine we're in and who called us. But how does it know that we were called from Factorial before? And if you have any local variable, it will be able to display local variables if you have a subroutine written in C. When it's in assembly, obviously that's not the case because it doesn't have the necessary label to find the local variables for the parameters. But way it works has everything to do with the frame pointer, EBP itself. Okay? So if you think about the frame pointer, okay, I have to do a picture here because it's really hard to do it in plain text. So if you think about the frame pointer, okay, let's say this is the first frame of everything, okay? And the first frame has the highest address because the stack grows to lower addresses. So somewhere in here is OEBP, right? So OEBP is going to be here, and this OEBP can point to whatever space. Okay, this is actually running out. Okay, let's try this one here. Okay, so this is OEBP, and it points to some la-la land. We don't really care because it is the first invocation. What about the second call frame? Second call frame can be larger, can be smaller, it doesn't matter because it depends on the subroutine and how many parameters are being passed to the second invocation. But somewhere in here is also going to be an old EBP. Where do you think this is pointing to? Right there. If I have a third invocation, doesn't have to be recursive. It can be main, calling F, calling G, calling blah, 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 whatever, okay? It has its own OEBP too. This OEBP, which used to be the frame pointer of the caller, is pointing to where? Here. And so on. So the next frame pointer has its own OEBP somewhere, and that points to here. Okay, that's great. But how do we know where we came from? Okay, the return address shows us that. But where's the return address? If you look at the picture that we have earlier, of all of the old pictures that we had earlier, where's the return address? How does it, is it always at a certain place? It's always right next to old EBP. So the return address is here. Return address is here, return address is here, return address is here. That is how BT works, okay? Backtrace looks at the current frame. It looks at the current EBP as the starting point, okay? And then it will know the return address. By knowing the return address, it knows who called us. Is that okay? But also using old EBP, it can also go trace back to the other frame, and it will apply the same method to go back to, oh, you know who called the previous invocation? It's this guy here. Go back to the previous one and go back to the previous one. Now the debugger also talks to the compiler. Okay, if you're dealing with like regular C and C++ code, it will talk to the compiler. The compiler leaves behind certain symbols as displacements to the local variables as well as the parameters. So if this is actually the frame, or these are the frames of a C program, or C program, then all the local variables which are under OEBP and all the parameters above OEBP, they can all be retrieved by the compiler, by the debugger. So as a result, the debugger can give you a backtrace in a C or C++ program to show you exactly how you got here. Now the other really cool thing you can do with the frames is you can use a command called frame, just F-R-A-M-E itself, and you can say, I want to go to frame 4, okay? And in this case, 4 refers to this 4 here. So now we can go back to frame 4, and at this point, because my current context is temporarily switched back to frame 4, if I have any local variable, any parameters in frame 4, I can now print every single one of them and access every single one of them here. And this is a very, very powerful technique of debugging, not your program in assembly so much, but your programs written in C and C++. Is that making any sense? Because if you have a problem with a subroutine, sometimes it depends on who called me. And this gives you everything that you need to know. Every time you're in the subroutine at a breakpoint, you can use BT and say, how did I get here? Who called me? And who called that? And you can retrieve the entire history of all that stuff. But it relies on two things, okay? Two things not getting messed up. What if you are to mess up OEBP somewhere along this line? This chain would be broken. What if you are to mess up your return address? Then it will report back the wrong caller, right? Okay, and when you actually get to the return, it will return to the wrong place. Is that okay so far? So I want to leave you with one question that you can kind of think it over the weekend. What kind of C code can mess up OEBP on the return address? Okay, we had a program like that from day one of this class, okay, because I was trying to explain why this class is important. So you might want to kind of go back to that sample program that I wrote, that I carefully crafted so that it would crash in a certain way. You might want to go back to that one, because this is kind of like a closed parenthesis to that open parenthesis. I know it has been a long time, but it is now connecting. I'm hoping that some of you are starting to see the connection between that really kind of simplistic program, but it crashes in a really special way, to what we are talking about right now. Okay, so the next question is, what kind of code can modify OEBP on the return address? The worst thing you can do to these two is not to put a 0 into it. If we put a 0 into it, it just crashes the program almost right away. Not right away, but almost. The worst thing you can do is to do a plus equal 4 or minus equal 4 or something like that. Then when you go back to the caller, the frame pointer is now off, but it's not completely off. It's off by 4 bytes. What used to be variable A is now variable B. What used to be variable B is now variable C. So when you look at the code, or when you trace through that code in C and C++, it's going to be very, very confusing. Okay, so we'll talk about this next time, because I'm pretty sure one of us somewhere along the line will step onto one of those landmines, and knowing this, we have the tools to debug that sort of thing. Based on the symptom, we know something happened to EBP. Okay, who messed around with my EBP? So they can track it down. Okay, so that will end today's lecture. I will be at the lab to help you guys with the homework assignment if you are starting on the homework assignment. And we'll let Mr. Fox's class in, because I'm pretty sure they're eager to come in.
It's cold out there.
Is it? I will take a look. That's a good idea. Has failed to process, that's why. So there's something wrong with the file. I'll try to rescue the file, then I get to the lab.
So she grabbed the external hard drive, and ran out of the car. Because we were just talking about it last night. Yeah. We were talking about what we take.
Okay, where's my recording for today?